So let's consider the case of a line of charge. Okay, so we got a line of charge here, and we are trying to figure out for this line of charge, what is the electric field at some point right here, a distance d from the end of the line of charge. Okay, and so we look at it and say, well, so there's a little piece of charge right here, dq, that's going to make a dE right here. There's another dq right here that's going to make a smaller dE because it's farther away. Another dq right here makes an even smaller dE. And so we need the total electric field is going to be the integral of all of those little differential fields. So we need to figure out what is that little differential field right there. And so we look at it and say, well, let's figure this. So here's my line of charge. So I have some Q and it's spread out along the line of charge. And so if the line of charge is some length L, then lambda is just going to be Q over L. Okay. Well, what if I don't know what L is? I might still know what lambda is. I know that lambda is the charge per length. So it might be, for example, that every meter of this wire has 2 microcoulombs on it. In that case, then lambda would be equal to 2 microcoulombs per meter. Okay, so that's what this means. That it is how the charge is distributed. So for our case, that's just an example there. But for our case, then we would look at this and say, well, in that case, then we would say that the lambda dx is going to be equal to the dq, because lambda is going to be dq over dx. That's just a little bit right here. Okay, so we got our wire. Okay, and we've got our spot right here, some distance right there. Okay, and so I want to know what's the electric field. So if I have some little dq right here, okay, some little dq, and so I know that the dE for that little dq is going to be k sub b dq over r squared. Well, what is r? R is that distance right there. Okay, so what is that distance? Well, what I can do is I can put my origin right there, and I can call that x right there. So r is going to be equal to x plus d. So that means r squared is equal to x plus d squared. Okay. So that means that for my little setup right here, that this is some d, that the dE is going to be equal to k dq over x plus d squared. Well, I know that dq is lambda dx. And so now x plus d squared. So E is going to be the integral of dE. So that's going to be the integral of k lambda dx over x plus d squared. And we'd go from 0 until the end of the wire. Okay, so the end of the wire. So how far is this wire? What I'm going to do to make the math easier is I'm going to assume that the end of the wire is infinitely far away. So that means I'm going to go, my integral is going to go from 0 to infinity. And so you ask, well, how can you have an infinitely long wire? That wouldn't even fit on Earth. Well, it doesn't have to be a mathematical infinity. This is what we think of as an engineering infinity. So if something is really far away, then the effect of it is going to be so minor that it's not going to be anything to worry about. For example, if my wire has an actual length and the length is going to be 8.25 meters, and if my distance is 1.1 centimeters from the end of it, then what that means is that whatever charge is here is going to be so close, it's going to totally dominate everything, and the charges at the other end are going to be so small, that's going to be out so many decimal spots that we never calculate that far. If it's like 4, 5, 6, 7, 8 decimal spots over, if that's where you're changing things, we don't normally calculate that far, and so we sort of kind of ignore that. So the statement that L goes to infinity is really a statement that L is much, much bigger than the distance right there. So that's really what that means. So my electric field, okay, is going to be equal to the integral of K lambda dq, or the dx, divided by x plus d squared, going 0 to infinity. So some of these things are constants, comes out of the integral, okay, and so this is just dx over x plus d squared. Okay, so now the question is, how do you do the integral x plus d squared? Okay, and there's several different ways that you can do this integral. Okay, one way of doing the integral is looking at it and say, okay, let me look at this and say, well, I look at the integral and I see, okay, so we got x plus d right here. The derivative of x plus d is actually just dx, and so this is actually not that hard of an integral to do. So this comes out to be k sub b lambda. When you do the integral, what you have is you've got minus 1 over x plus d. Okay, and we evaluate at 0 and infinity. Okay, well, obviously at infinity, if x equals infinity, the limit is going to be 0, so that means this is going to be equal to k sub b lambda, basically 1 over d. Okay, and so and the direction is going to be to the right, okay, if lambda is positive, so that's going to be in the I direction. So we would say that the electric field is k sub b lambda over d in the I direction, so to the right. And so that's the answer. This is what we call the semi-infinite wire. So the wire has an end point. We are some distance d off the end point, and the other end is infinitely far away. Okay, and again, this is engineering infinity, not math infinity. This means that it's just simply so far away that the other end does not contribute appreciably to our calculations. So where would you ever use such a thing like that? Well, one similar sort of thing, situation is, for example, for lightning rod. Lightning rod is not exactly a wire, but it's a long, spiky sort of thing. And if you build up electrical charge on there, that creates an electric field off the end of it. And one of the things we discover is that that electric field right there is what is discharging. And so we'll talk about how that works later. But this is an example of where you would actually see this sort of configuration.